Hello Kidlets, and we're continuing with your lecture notes for Chapter 2 in the unit of Sky and Scale. This section is on the celestial sphere and why we see what we see overhead. So just as a review, remember that the direction directly above us is always going to be our zenith, and opposite of that would be our nadir. Sorry, that was in black, kind of tough to see. And that's going to depend on where we are globally. Remember that this whole concept of a celestial sphere as opposed to a celestial square is because the limit of our horizon is always in the shape of a sphere. And this is kind of an ancient concept going back to this whole concept of the entire universe, which is what it was thought of at the time, rotating around us and attaching all of the stars that we see and every object that we see to this sphere, which was the same as what ancients called heaven, and thinking that that entire sphere rotated around us. So the reason that we see the stars moving is because obviously the Earth rotates. The Earth rotates and that changes our perspective. So we know that Earth rotates from west to east. So that means that it appears to us as though the sphere rotates from east to west. Therefore, we see things rising in the east and setting in the west. So it appears to us as if all of the stars are attached to the sphere, and that this path is like a latitudinal circle. But we know, obviously, that the stars are not all attached. They are not equal distance from each other or from Earth. So some of these locations, remember that our zenith is directly overhead, opposite to nadir, which is directly beneath your feet, and we can never see our nadir, ever. Just like for the northern hemisphere, we can't see our south celestial pole. Then we have the horizon, which will be the lowest place that we can see. Remember, if a circle is 360 degrees, we can only see half of that, which is 180. And the horizon is halfway between each of these two, your zenith and your nadir, because one is up, one is down, so the horizon would be right between. And then we know that we have this north celestial pole. I apologize, this program totally skews my formatting. That shouldn't be next to it. But we know that the north celestial pole is where our rotational axis is projected onto the sky. South has one too, which would be the southern rotational axis, which we can never see. So those would be the NCP and the SCP, and I have no idea why that bullet point is next to it. I apologize. I'll be griping about that all semester. So one of the other locations we have on the celestial sphere is the celestial equator. So if we were to draw our celestial sphere here, remember that lines of latitude divide the Earth into north-south. So we can remember that our equator would be right about here. It would be right in the center. So the celestial equator is just the projection of that onto the sky. So this other idea is this concept of a meridian. Now, we did not talk about this in class, but I will tell you that for your moon observation, you have to know where this is. So we can think about the celestial meridian as dividing our sky, connecting our zenith, I love the lightsaber pointer, our NCP and SCP. So this is, again, a way to divide our sky. So if we look at up here, there would be our observer's zenith. So here would be the south celestial pole directly below it, and the celestial meridian is just going to chop our sky in half. So that is also going to then intersect the celestial equator. So it's going to cut it in half, and it is directly over the south. So from zenith to from our NCP to the SCP, it's going to go through our southern and our northern horizons through the celestial equator. So we can see, looking at Earth inside the celestial sphere, there's our little dude, there's his zenith. We can see our rotational axis projected onto the sky. There's our north celestial pole, our south celestial pole. Then if here is Earth's equator, right here, that projection onto the sky would be right here. So the celestial equator, the terrestrial equator, are just parallels to each other, one on Earth, one in the sky. And the thing to remember is, just like Earth's equator is between the north and south, so is the celestial equator between the two poles, the two rotational axes, but in the sky, so the NCP and the SCP. So again, that celestial equator is a projection of our equator onto the celestial sphere. And here's showing a lot of those coordinate systems again. And the thing to keep in mind is that our pole star, like we said last time, our pole star is not a very bright, not a very spectacular star, nor has it always been our pole star. It is our pole star due to positionality. So the altitude of the pole is equal to the latitude of the observer. And remember that latitude, like we said before, separates the Earth into north and south of the equator. So we can determine what latitude we're at by the positionality of the North Celestial Pole. And this is the way that people on the ocean, this is still used today, how people can determine which direction they're going, because even GPS often doesn't work in the middle of the ocean because there's not a whole lot of communication satellites that are directly above them, and that's the way GPS works, is it has to talk to a satellite. So this is still how people can find their way. This is how people navigated on the seas thousands of years ago, was measuring the degrees above the horizon to the North Pole or the South Pole, and that determined their latitude. So a general rule is that the altitude of the pole is equal to the latitude of the observer. So for an observer that was at 40 degrees latitude, the latitude of the North Pole, or altitude of the North Pole, would be 40 degrees. So the circumpolar zone that we'll talk about in a second depends on the latitude. So those would be the stars that surround either the North or the South Celestial Pole. So such as these star trails that we can see right here. And stars that surround the pole star, or constellations that do, that generally never rise or set unless you were like here at the equator. So here we can see with an example of New York City that has a latitude of about 40 degrees. That would mean that the celestial North Pole from New York City would be at exactly the same latitude. So that's where we would find it in the sky. So here are 4 different examples. So here if we look at our observer that is at, just like it says, 90 degrees. So if you remember our positions of latitude, we can remember that 0 is equal to the equator. So that means 90 has to be the North Pole. So if that's the case, if this is 90 degrees of latitude, then the zenith and the North Celestial Pole are in the exact same place. So that would mean then that the celestial equator would just intersect that, because the celestial equator is going to intersect the rotational axes. So here another example. So we've got latitude of 30 degrees. So this would mean that the pole star is going to be about 30 degrees off of the horizon. So here we can see our celestial equator. So if we were to draw in where the terrestrial equator is, it would be right there. So sorry, that's a terrible line. And here it would be smack in the middle. So we could see the celestial equator would be just the projection then of where that is. And just remember that just like on Earth, the equator divides the Earth into north and south. It does the same with the sky. So once you can find north and south, or your north and south celestial poles, you can find the celestial equator. So zenith never changes. That is always overhead, such as this. But your pole stars would then be dependent on your latitude. So here another one. This is 0 degrees. So remember that that tells you it's the equator. So here, if you're at 90 degrees, that would mean that the North Celestial Pole would be on your horizon. The South Celestial Pole would be on your other horizon, and your celestial equator would intersect your sky perfectly. Now this would be southern hemisphere, so this would mean the North Celestial Pole can't be seen at all. So there's no NCP. But this would mean that the South Celestial Pole would then be, just like this is 30 degrees, this would be 30 degrees off of the southern horizon. But there's still a zenith. It would just not be as, it would be the same as our nadir. So looking at some different distances. So we can measure the distances across the sky by breaking the sky apart into degrees, minutes, and seconds. So we know that in a circle there are 360 degrees. We can then further break that up into minutes, and this is supposed to be the degree symbol there. So 1 degree is equivalent to 60 minutes, and then 1 minute is equivalent to 60 seconds. So this just allows us to further break up the positions of stars in the sky from constellations or regions of sky into approximately quantifying where exactly a star or an object, if it's something that's not a naked eye object, where to look. And especially for things like asteroids. You can't see asteroids with the naked eye because they're so dim. They're usually a magnitude of 16 to 20. Or deep sky objects. This would be, a way to tell where those things are. And this is the way to measure that. So, and this is what you guys will be using for your observations. So you can see that generally, one finger, your pinky finger, unless you have monstrous hands, even if you do, use the same sort of rule. But generally, your pinky finger is equivalent to 1 degree, and the biggest span that you could measure would be thumb to pinky, which would be 25. So this is generally how you will be using measurements across the sky for all of your observations, from your moon observation, your observation numero uno, and also your solar observation. So best to attempt to at least remember 1 degree from 25. So you'll be holding your hands up to the sky during your moon observation to try and quantify how far objects have moved. You'll also be picking a reference star and trying to gauge how far that reference star has moved from the moon and its distance from the moon each night, because your reference star is not going to appear to move. The moon, since it's so much closer to us, it'll move somewhere between 10 and 15 degrees every single night. Declination and right ascension are coordinate systems on the celestial sphere. However, just for making things simple and easier, I just want you guys to know what these are. We're not going to apply them. We will be using altitude and azimuth. We will not be using declination, right ascension. These are a little bit more complicated, and I only want you guys to get used to using one system. When we go to star parties and we're aligning telescopes, they will be using altitude and azimuth because that moves with the sky, whereas this doesn't exactly. So what we can remember is that declination is equivalent to latitude, and right ascension is equivalent to longitude. So, and we can remember that, again, latitude, so there's the equator, that's a latitude 0. So our latitude runs north-south, our longitude runs east-west. So just like longitude breaks the Earth up into east and west of the prime meridian, right ascension does that as well. There has to be a starting point. So just as the longitude system starts above the Greenwich, England, that's where right ascension starts from as well. So these are just projections of latitude and longitude upon the celestial sphere. That's all you need to know. We're not going to be applying those. You just need to know what they are. Altitude azimuth is what we are going to be using. So I've mentioned altitude a few times, which is how high in the sky something is. And this is measured in degrees. And azimuth is our other directional system, which tells us we are facing either north, south, east-west, or south-southwest. And that's also measured in degrees, but the starting point is north. So the value we would give north is 0. North is 0. So if we are facing directly east, we would be at 90 degrees. If we were exactly south, it would be 180, because remember, this is all based on a circle of 360. So if we were facing then west, would be 270. And I think I gave those values to you right here. So we could tell exactly which direction we are looking in based on the degrees of azimuth. So altitude is how high up or down. Azimuth would be degrees from north, or east-west is the other way to tell. So we have up, down, east-west, side to side. That's what our altitude azimuth system tells us. So here is what that looks like. So we could see altitude is measured in degrees from horizon. So remember that horizon would be an altitude of 0. Zenith, directly overhead, would be a value of 90, because it's exactly a right angle. So this star is directly between. So I'd say this is an altitude of about 45. So then we can see in terms of azimuth, north would be 0. Our east would be 90. So this star is, again, about between that. So I'd say this is probably 40 or 45. Looks like it's a little more northernly. So I would say that this is an azimuth of probably 40 degrees. Somewhere between there. So if I gave you a picture like this and assessed you on that, I wouldn't give you choices of 40 to 45, but you would need to know that it's not 0, it's not 90, it's not 180, that if it's between north and east, it's got to be between 0 and 90. And for your altitude, the highest it can possibly be is 90, and the lowest it can be is 0. So your altitude is just your degrees above. So if it's exactly in the middle, you know it's got to be somewhere around 45. So that would mean that this star, if this, say, were our North Star, that would mean that this observer was at a latitude of 45 degrees. Now, this is just a sample star, but if it were the North Star, that would be the latitude. So we can also see stars that rise, set, and transit. So looking at these star trails, time-lapse pictures of the celestial sphere are really pretty because you can see all the different colors of stars in the sky. So we know they rise when they move above the horizon, they set when they move below, and their period of transit is when they're moving past the highest point in the sky, or in this case would be right about this location. I believe this is either Mauna Kea in Hawaii or the Palomar Observatory in San Diego. From night to night, minute to minute, hour to hour, if we were to look up at the sky, we could see that it appears as though the entire sphere itself is moving. And this is what gave way to this whole concept of an Earth-centered or geocentric system, in which it appeared that the sun, moon, stars, and planets all appeared to move around the Earth. So if we were to just look at our pole star, so we could see that everything appears to track around it. So we would call these constellations that lie very close to the pole star our circumpolar stars or circumpolar constellations. So in this case, there is Polaris, that's our north celestial pole. Ursa Minor, which we call the Little Dipper, the last handle star is what is Polaris. That is where it is. So we can find that also by looking at Ursa Major. The star in the bowl points directly to it. So that's the other way that we can find it. I think about the Big Dipper dumping into the Little Dipper, or sometimes when it's the other way and the Little Dipper is pointing this way, it's dumping in. But they're dumping into each other, and the last handle of Ursa Minor is where you'd find Polaris. So if we were looking north, we would see the stars apparently moving counterclockwise as they circle the pole star. Here we can see a good example of some circumpolar stars. So here would be Polaris. This one, I believe, is in Palomar in San Diego. We can see all the different color stars, so we can see some reds, some blues, because not all stars are just yellow like our sun. But all of these that track around, that you can see complete a full circle, never set below the horizon, those would be our circumpolar stars. So here gives a good indication of what sort of latitude this is, because we can see the horizon, and we can see this star right above. That looks like about 35-ish degrees, which is exactly what Palomar is. So here's a few circumpolar constellations. So for our sky, these are ones that really never rise or set. And we can tell which direction of sky we're looking at if we were to observe some pictures of star trails, because if we were looking east, remember that everything in our sky appears to rise in the east, set in the west. So we would see stars that appear to be going upward. Then if we look south, we're going to be observing their period of transit. So it would look like they were moving towards the right. And then contrary to that, if we were looking due west, we would see them moving down. So if we see them moving up, we know we're looking east. If we see them moving across, we know we're looking south. If we see them moving down, then we know that we're looking to the west. So that is all for your notes, guys. Please make sure that you have your notes and summaries done by the end of this week.